We're going to get into probability now and the next section, and it's actually, if you're curious about taking eventually an AP Stats, AP Calc, we're going to be using a lot of these in both those classes, and it's not all every day that we do both lessons into these, but that's eventually what we're getting into in Unit 11. And before we get into we're pretty far away still from talking about all the stuff that's in advanced placement classes, but probability, it basically shakes down to the number of outcomes for an event over the total number of outcomes. Don't be surprised if you ever hear me say it's what you want out of the total. And I'm not sure how much experience you got of this in Algebra 1 or even middle school, but probability basically shakes out to the chances of an outcome happening. That's what I mean by what you want, out of the total sample space, which is where we're getting into exercise 1, where they're trying to get you to I guess, think about it. So we're trying to determine how likely it is that a mouse will correctly get through a maze. He has to take, or she has to take 3 turns, right or left, to get through the maze, and only get cheese at the end if it makes 2 lefts and a right in any order. So if you think about it, you can make a tree diagram on how this maze goes. Now I'm going to, I guess, kind of split it up where each one is left and right. So this is what we mean when we say make a tree diagram. Left and right, but we actually have 4 possibilities because right here is also a left and right. And at this point I think I'm just going to write L and R for each one. L, R, L, R. And what you can see is that we have a total of 8 possibilities. Now that's a tree diagram. Sometimes what we'll do is a sample space with our roster notation. So each one of these, maybe I'll just highlight one of these in blue, that we go left, 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 L, 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 which would be different than going left, left, right, L, L, R, which would be different than going left, right, left, left, right, right. I'm just kind of going in order. Right, left, left, right, left, right, 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 left, and then right, right, right. That's what they meant by ordered triples. And that's a sample space. Sample space. So how many total outcomes did we get? We got a total, I'm just kind of jotting that down while I'm going through the problem, because we're going to eventually need the total number of outcomes. But if we read the directions again, we wanted 2 lefts and a right in any order. So I'm just going to circle 2 lefts and a right, 2 lefts and a right. Let's see, 2 lefts and a right. I think that was it. I guess I could list it again. I was just circling left, right, left, or right, left, left. And I have no idea how this maze is set up. But you can see my phrase of what I want is 3. So what's our final probability? It's what I want out of the total, or the number of outcomes where the event is satisfied over the total sample space is 3 out of 8. And we get this phrase of equally likely because maybe there's a probability, like maybe one pathway is smaller, so the mouse avoids it or something like that. But anyway, 3 out of 8 is what we wanted. So here's another situation where Carlos is trying to grab 2 dimes out of his pocket. He has 2 dimes and a penny. And if he randomly grabs the 2 coins without replacement, what's the probability he gets 2 dimes? So basically what's happening now is he reaches into his pocket and he grabs a coin. Well, he has 3 options at first. let's see, dime, dime, penny. Well, if he grabs a dime first, now there's only, because it's without replacement, it's either the other dime or the penny. And then this situation, it's either the dime or the penny. And in this situation, it's either dime 1 or dime 2. So if I'm drawing a tree diagram to list out the sample space, there's only 6 options now. And what it shakes out to is the probability is either going to be dime, 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 penny, dime, 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 penny, penny, dime, or penny, dime. And if you're trying to figure out what's the probability of getting both dimes, there's only 2 of those out of the 6. 2 out of 6, or 1/3. If you're kind of curious, what some people will do is they'll actually name the dimes as well, like dime 1, dime 2, and if it helps you, dime 1, dime 2, that like you could name each one of these. If that, I don't even know if it is helpful. Like maybe you're getting dime 2 and then dime 1, dime 2, dime 1, dime 2. But anyway, this next exercise is sort of difficult to do on a video, and I'm not sure if we'll even do this in class. But what the thought process here is to set up a situation where you're playing a 3-person version of rock, paper, scissors. And basically, we want to shake it out to see if player A wins. So 3 people, so player A, B, and C. Well, player A wins if all 3 play the same one. Player B wins if all 3 hands are different. And then player C wins if the 2 hands are the same. So we could do this as a class. We could probably do this as each one. But we want to, I guess, see each situation. So what I'll just do is rock, paper, scissors, R, P, and S. And we can shake it out where that's player 1. So maybe in green is player 1. Maybe in blue I'll do player 2. Rock, paper, scissors. But equally as likely as playing rock, paper, and scissors here, but then equally as likely rock, paper, and scissors here. But then we have to have player 3 could do rock, paper, and scissors. Rock, paper, scissors. I'm kind of getting tired of doing this. And I'm running out of space. I knew I was going to do that. Rock, paper, scissors. But what might be helpful is to start thinking about how to do these problems quickly. And if you look at that pretty quick, we're going to learn this pretty soon. But in this tree diagram, what you'll see is that we have 3 times 3 times 3. We'll summarize this again later, that there's 27 as your total sample space. But if we're trying to see if player A wins, now remember, player A wins if all 3 are the same. So that would have to be rock, rock, rock. It could be paper, paper, paper. And it could be scissors, scissors, scissors. And so the theoretical probability, so in theory, player A would win if there was 3 out of those 27 games. So probably pretty unfair for player A. Now for player B, let's remind ourselves how player B wins if all 3 are different. So as you're looking through all of those, the tree diagram, rock, well, it can't be rock now, so it could be paper next, and then scissors. So R, P, S. Let's see, rock could be scissors if the next one is paper. So rock, scissors, paper. So the next one, paper, rock, scissors. Let's see, it can't be paper a second time, so we'll go to paper, scissors, rock. So you can start to see that this is probably unfair let's see, scissors, paper, rock. And I'm going to skip the next one because if that's scissors, it can't be scissors the next one. So player B has double the amount of probability of winning, 6 out of 27. And you could reduce that as well. I believe that reduces to 2/9. But here's another thing for you to think about. Instead of counting up how many you have left, what you could do is just say, okay, well, if player A has 3 of those winnings, player B has 6 of those winnings, that's a total of 9. The remaining 18, why 18? Because 27 minus 9 is 18, is the number of outcomes left over for player C, because somebody has to win, either A, B, or C. So this game is unfairly, I guess, going to result in player C winning. And I believe that reduces, because they're both divisible by 9, to be 2/3. Yeah. And hopefully that's pretty straightforward so that you can start the homework in section 1.